right, it looks like we're almost ready to go. So I'll introduce our next speaker. So Karta Kooner is coming to us from Dyalog. Karta came to APL by accident via code golf and is now deep in the Dyalog interpreter as a C developer. He is now one of its most enthusiastic supporters, especially in technical and academic spaces. He will be speaking to us about the challenges found within APL standardization. Please help me welcome Karta.
Hello, my name's Karta, and as Julia said, I'm a C developer working on the APL language interpreter at Dyalog. And today, I'm going to give a quick history of APL and Dyalog's place in it, and where the standards came along. My talk's going to be slightly different perspective than Adam's talk earlier, if anybody attended that, which was my presentation is going to be about how issues in the APL standard affect my life as a developer of the interpreter. And I'm going to go through 3 examples with you about how issues with the standard affect my life. So I'm going to go through some differences between different APL implementations. I'm going to talk about an omission in the APL standard and how that affects me. And I'm going to go through another example where we choose to diverge from the standard. Okay, so before I begin, how many people here had seen APL before today? Okay, that's actually more than I expected. Okay. Well, for those who haven't seen APL, this is what APL looks like, or what it can look like at least. Most of you can probably tell that there's a function being declared here, but the body of the function is probably incomprehensible to most people. There's a lot of funny symbols going on. Well, these symbols are the fundamental elements of the APL language. In the APL jargon, they're called primitives, primitive functions and primitive operators. They have a slightly technical difference, but I'm just going to be calling them operators in this talk. Each of them performs some sort of mathematical or data transformation to the arguments given to them, and they have a binary or unary form. Some of them are you could figure out what they do, and some of them are much more complicated. Okay, so APL is an array programming language. It's interpreted, and it was developed by Kenneth Iverson in the 1960s. I'm going to give a quick overview of the timeline of APL's evolution and where the standards came in, so you can have an idea of how the standards have affected APL vendors and implementations. So in 1962, Ken Iverson publishes a programming language whereby APL derives its name. IBM released the first implementation in 1966 called APL 360, followed by APL 1130. There are a few more implementations by different vendors extending the APL language. And in 1979, IBM produces the first standard, which they had been working on at the APL 79 conference. In 1981, NAS releases their interpreter, which incorporates nested arrays, and I'll talk more about nested arrays later on. We came about in 1983, initially known as Dyadic. IBM produced an implementation called APL2, which was their take on nested arrays. Arthur Whitney produces A, and then the first ISO standard appears in 1989, not using nested arrays, but what are called flat arrays. Then follows 2 APL-like languages called J and K. And then in 2001 is the second standard, the extended APL standard, which incorporated nested arrays, which were introduced 20 years earlier. We have a successor to NAS called NAS 2000. We have GNU APL released. And this is the timeline of APL's evolution and where the standards appeared. So what I really want you to take away from this is that there was a lot of development of APL both before and during the standards. So today we have Dyalog APL, that's me and Adam earlier. We have IBM's APL2, we have APL64, APL plus Win. We have NAS 2000, GNU APL, and Zyma APL as open source releases. And we have about half a dozen other smaller vendors doing development or experimental work. Okay, so that was a brief introduction of APL's history and where the standards appeared. So let's talk about the first thing I want to talk about today, which is differences in the APL standards. Differences within the APL implementations. Okay, so in APL, in order to produce an array, you don't need any special syntax or decoration, as Adam in the earlier talk mentioned. You just need values juxtaposed next to one another, separated by white space, in order to produce a vector or a list or a one-dimensional array. I'll use these terms interchangeably. So this declares a vector 1, 2, 3 and assigns it to the variable x using the left arrow. We can take this vector x, we can add on to another vector in the 3-element vector, and that will produce the expected output that you would normally expect. We can also add a scalar to a vector. So this will add 10 to every element of the vector through a formal process called scalar extension. But this will take the value 10, add it to every element of the vector x, 1, 2, 3, producing 11, 12, 13 as its output. Okay, good. I mentioned nested arrays. A nested array is an array whereby one or more elements is itself an array. We could produce here a nested array through a process called stranding. Now, stranding is where two or more arrays juxtaposed create an enveloping nested array that contain the initial arrays as inputs. So this produces a 4-element array. The first element is 1, second element 2, third element 3, and the fourth element is the subarray 4, 5. And just to stress that point, we can add on to that array an explicit 5-element array, 1, 2, 3, 4, 5, and that will produce a length error in APL. You can only add arrays of equal lengths other than scalars through this process of scalar extension. Okay, good. We can also do indexing using the square bracket notation, which hopefully everybody here will be familiar with. So this will extract the second element of the array 10, 20, 30, producing the output 20. Okay, so what about this one? What do people in this room think will be produced by this expression? Everybody's too shy to answer. Yeah. Okay. Well, most people in this room were wise to not answer because it's a trick question. Of course. There's two things going on here, right? There's the stranding that you saw in a previous slide, and there's indexing. And the APL standard doesn't specify an order of precedence of these operations. So different APL implementations will do different things. Dyalog will do the stranding first and form the nested array, then take the second element of that array. Other APL implementations will do the indexing first. So the indexing is attached to the subarray or to the array 40, 50. It will select the element 50 and then strand it to 10, 20, 30. So this is an issue where the APL standard not specifying the way to pass the token stream causes issues for implementers like us at Dyalog, where we have to sometimes port code from other implementations, and this causes us lots of issues. Okay, let's take another example. This circle symbol between plus and 1 is called the bind operator. And what it does is it binds the value 1 to the binary function plus. We then assign this function a name called successor, and then we can call successor with the value 2, for example. 2 will get passed along to this function, and it will just add the value 1. And I hope that's clear to everybody here, what's going on here. We saw before that we can add scalars to arrays. So if we pass an array to this function, this will feed into this, what's now a unary function, because we've bound one of the arguments to plus. So this will compute 1, 2, 3, 4, 5 plus 1. And so that will, through scalar extension, we will add 1 to each of the elements of the array, producing the array 2, 3, 4, 5, 6. Yes, do you have a question?
So this seems to depend on successor being a function, but that is only something you know dynamically, right? Like,
yeah, so successor is only known dynamically. Yeah, that is one of the issues in APL, yes. In order to execute this line, the interpreter needs to know the definition of successor. Successor could be a variable, and then stranding would occur. This occurs all the time in APL. I mentioned before the difference between APL functions and operators. So an operator is formally something in the mathematical sense is you probably more know as a functional, something that takes a function as an argument. And again, you would need to resolve the names of the objects in order to know whether you have an operator taking a function or whether you have a function taking variable names. So yeah, so that is an issue that APL deals with all the time. Yeah.
can actually construct a list of functions.
Can you construct a list of functions? Yes, you can construct a list of functions.
How would that work syntactically?
How would that work syntactically?
So successor and successor. The two-element list, just a list of functions that would look like an application.
Yes, yeah. Yes, I think that would work perfectly fine, I think. You're asking me to think on the spot. So, yeah, I mean, I think it should work just fine. I can.
It just seems syntactically ambiguous. I mean, it could mean both, right? Like there's no clear way to.
Well. If you had just successor and successor forming an array, that would just be an array of functions, right? Where's the ambiguity? You would need some value in order to.
So why is it not the application of successor to successor?
Okay. So that is. Because that's just how the syntax works, I think is the answer to your question. But I can double check that for you afterwards. You come talk to me afterwards. Right, okay. Right. So we've seen before that we can add scalars to arrays. We saw that we can bind the scalar 1 to the plus function. We can also bind an array. But we get the same issue, which is that the APL standard does not specify how this token stream should be passed. One option is to first construct the array 1, 2, 3, and then bind that to the plus function. Alternatively, implementations can bind the value 1 to the plus function, and then feed the values 2, 3 to that function. So Dyalog takes the former approach. If you enter the expression in the middle, it will return back. It's an anonymous function, so Dyalog will just return back the definition of that function. Different implementations like NAS 2000 will take the latter approach and pass the input as a function with the value, with the array 2, 3 fed to it. So it will it will do 2, 3 plus 1 and return the value 3, 4. So again, this is an issue whereby the lack of the standard specifying exactly how to pass expressions, lines, leads to different behaviors by different implementations of the same APL expression abiding by the same standard. And so that causes issues for us when we're porting code from other implementations. We have various strategies, but it makes our life harder doing this. Okay, so that was differences in APL implementations. Let's move on to another example where there's an omission in the APL standard.
All the differences like party related?
The question is, are all the differences passing related? No.
Is it
there are also
for a second? Karta, do you want questions while you're talking right now, or would you rather have them at the end?
The answer to that, I'd rather have them at the end, only because then people who are watching this back might not hear. But I don't mind either way. I can repeat the questions so that people. So no, that's not the only difference. There are differences in primitives. So there are certain primitives that behave differently from various implementations. And we have various strategies to deal with that. But yeah, it's not the only difference between implementations. But I thought this was quite a nasty one that we have to deal with. So it will be interesting to talk about this today. Okay, so next example I have here is an omission in the standard. So if you were here for Adam's talk earlier, he talked about the new array notation, which is going to be in version 20, which is going to be released imminently. This declares a 2x2 matrix, 4213. And we can use this funny symbol on the left here, which we colloquially call domino. But what it does is matrix inversion. And you can think of this as a box to divide symbol, if you can see that. I think of it actually more like a block matrix. So you have a block on the top and a block on the bottom. But anyway, this symbol does matrix inversion. So we'll invert the matrix 4213 and produce the matrix that you have there. We can also extend matrix inversion to non-symmetric matrices. So here we have a 3x2 matrix. We can pseudo invert this to form a 2x3 matrix. And this is the Moore-Penrose pseudo inverse. Now, it's a bit late in the day to be doing advanced linear algebra, so I'm just going to mention that we can do inversions of non-symmetric matrices as well. Okay, so let's talk about a bug that came across my desk a few weeks ago. So we have this diagonal matrix here, 10 to the 6 and 10 to the minus 6. APL uses a high minus sign, so this just means 10 to the minus 6. And we can invert this matrix quite trivially to form the matrix below. Okay, let's scale these values up by 10 and the other one down by 10. Let's take 10 to the 7 and 10 to the minus 7, and let's invert that one. What do we get? We get a domain error. Okay. Why is that? Let's take a look at the standard. The standard for matrix divide says, well, first there are a couple of error conditions. So it says, if the rank of A or the rank of B is greater than 2, signal a rank error. That basically just means verify that the inputs to this matrix divide operation are matrices, two-dimensional arrays or less. There's a couple more of these. And then eventually we get to use the implementation algorithm matrix divide to generate an array Z. Okay, what's an implementation algorithm matrix divide? Implementation algorithms. An implementation algorithm is an algorithm used in this international standard whose behavior is implementation defined. In other words, the standard does not specify how to do matrix inversion. Now, on the one hand, you might think, well, matrix inversion is a well-known process. Everybody knows how to invert a matrix. But we've already seen how we extended, or certain implementations have extended matrix inversion to do pseudo-inversion for non-symmetric matrices. Now, that's not a unique process. There are different ways to form pseudo-inverses. So this is one place where the standard not specifying what to do can lead to differences between implementations. But we also saw the example before where Dyalog was producing a domain error here, and different implementations are quite happy to form a result. Now, what's going on here is the value 10 to the minus 7 is 14 orders of magnitudes smaller than the other value. And what Dyalog is doing is basically saying, this value is probably 0. You probably meant 0, and this was just a finite precision floating point error. You probably meant 0. That therefore makes this a singular matrix, and therefore I'm going to return a domain error. But we have no guidance from the standard. Is this what Dyalog should be doing? Should we be doing what these other implementations do? We have no guidance. This is probably a bug. It probably will get fixed, but it would have been nice to have seen the standard tell us what to do. There are other subtle cases, like if we take this 0 matrix here and we try to invert this, Dyalog will quite sensibly return an error here because it's a singular matrix. It's just got zeros in it. But other implementations give special values here. And again, there's no guidance from the standard. These are differences produced by APL implementation, different APL implementations. And if we're porting code, then we might have to deal with certain values like this. Okay, so those were two examples of omissions in the standard and the sorts of issues that it can cause writers of interpreters like me. Let's go through one final example where we choose to diverge from the standard. Okay, so we saw before that assignment is done with the left arrow. In APL, equals always does comparison. So here we're asking, does the value 1 equal 0.9999999? In APL, this will return the value 1. APL doesn't have a dedicated Boolean type. It uses numerical 1 for true and numerical 0 for false. You might be thinking, well, okay, this is an interpreter that's built in C. There's probably too many 9s here. And if you try and put this into a 64-bit floating value in C, then it's going to round up to 1. And so obviously 1 equals 1. But if we write this expression explicitly as 1 minus 10 to the minus 14, hopefully it should be clear to most people here that there should be enough bits of precision in a 64-bit float for the value 1 and the value on the right-hand side here to be distinct. So this produces in APL the value 1. Now, you might be more familiar with the classic example of 0.1 plus 0.2 in floating point not equal to 0.3. Again, in APL, we produce the value 1 here without using arbitrary precision types. The way we do this is that we have this concept in APL called comparison tolerance. The definition of comparison tolerance is this. And again, it's a little bit too late in the day to be doing math, so let's draw some pictures. Let's forget about this factor of max for the time being. If we pick a value x in the complex plane and we draw a circle of radius epsilon, then comparison tolerance says that all values y in the circle will be tolerantly comparable to the value x. In layman's terms, they're close enough to the value x that it was probably a floating point precision rounding error in your calculation. The factor max, which multiplies epsilon, simply increases the radius of that circle as your value increases. So we are always doing a relative comparison between X and Y here and not an absolute comparison. That's basically what's going on. Now, there's a subtlety here, which is that if the radius of tolerant comparison increases as your value X increases, then at some point it's going to swallow up into distinct integers that were adjacent to your value X. So if we draw some values here, which are integral values, then if your value X is big enough, then it will be tolerantly equal to X plus 1 simply because the radius has grown big enough to swallow up subsequent integers. Let's see this in APL. So this is a system variable called quad CT. Now, system variables are not technically part of the APL language, so I'm not going to talk about them further than to mention that they exist. So quad CT is the system variable that quantifies epsilon in this equation above. And by default, it has the value 10 to the minus 14. Therefore, if we compare a number that is 10 to the 14 with 10 to the 14 plus 1, these two values will be tolerantly equal. So these are distinct integral values. It is, what is that, 0.1 trillion and 0.1 trillion plus 1. And these are sufficiently close together that APL will say that these two values are equal or tolerantly equal. And you can stick this into the equation above, and you can verify that's correct. Or you can say, well, you can think of it as, this is a big number, right? 1 with 14 zeros, and this is 1 with 13 zeros and a 1 at the end. So the 1 at the end is close enough to 10 to the 14 that these values are probably, you meant them probably to be equal, and this was simply a rounding error. So that's what's going on here when we're talking about comparison tolerance. Okay, let's talk about flaw. So this symbol is the flaw symbol. It's 1/2 of the normal mathematical notation for flaw. Flaw, you should all know, it returns the greatest integer less than or equal to the given input. So the biggest integer less than or equal to 1.5 is 1. The flaw of 1.5 is 1. What about this input? Flaw does an implicit comparison tolerance. So if you type this into an APL interpreter, it will return the value 1. The flaw of 0.99999 is 1. Why is that? Well, because this value is tolerantly close to 1. You probably meant the value 1 here, and this was just a rounding error in your computations. The flaw of 1 is the value 1. Let's take a look at what the standard says for flaw. For real numbers, Z, the result, is the greatest integer tolerantly less than or equal to B, uses comparison tolerance. And again, let's contrast this to mathematical flaw. Mathematical flaw says the result is the greatest integer less than or equal to B. The APL implementation, because it uses comparison tolerance, says the greatest integer tolerantly less than or equal to B. Okay? Right, so let's put together everything that we've said so far. And let's therefore compute the flaw of 10 to the 14. As I said, in APL, this will take this, according to the standard, this should return the greatest integer tolerantly less than or equal to 10 to the 14. And we saw before that 10 to the 14 plus 1 is tolerantly equal to 10 to the 14. So, according to the standard, if you take the flaw of 10 to the 14, it should return the value 10 to the 14 plus 1. So something like 1.00001 times 10 to the 14. This, to us at Dyalog, doesn't make a lot of sense. If we did this, we think a lot of developers would just be filing bug reports. This looks like the wrong answer. So at Dyalog, we return the value 10 to the 14. The floor of 10 to the 14, it's an integer, it's integral. It will return 10 to the 14. Now, I'm being a bit blithe. APL is a mathematical notation, so we have actually thought about this. We have looked at the mathematical properties of the floor function, and I'm aware that everybody is now reading this, but you don't really have to. You just need to take away the fact that we have thought about the properties of floor that we would like to preserve in our implementation of floor, the mathematical properties of floor. And we think that our definition makes more sense in the sense that it preserves more of these properties than the standard does. So this is one example where we think our definition of floor makes more sense than the standard does. So here we choose to diverge from the standard. Okay, so let me wrap up. I've gone through a lot already, and I don't really want to frazzle anybody's minds anymore. I talked about the differences between APL implementations and how this has been caused by a lack of the standard specifying how to pass the token stream that's given to the interpreter. I've talked about where I think that there's an omission in the standard where this will cause problems and differences between different implementations, different interpreters of the APL language. And I've talked about divergence from the standard and why we choose to do that. And my main point here today was basically just to give an idea standard affect me as a developer. Writing standards is a non-trivial process, but do a better job so that people like me aren't complaining about it. And that's really all I have to say. Management at Dyalog have commanded me to tell you that if you're interested in learning more about APL and via challenges, via puzzle solving, and winning some prizes whilst along the way, you can do the challenge at challenge.dyalog.com. If you have ideas for libraries, tools, applications that you think you want to produce in APL, you can submit them to the Forge and we will give you, I think it's £2,500, so over 2,000 euros or dollars, and we will help you bring your idea to fruition, and we'll provide a little bit of guidance. That's at the Forge. And if you just want to learn more about APL, there's videos at Dyalog TV. And if you want to ask questions about any of the issues that either me or Adam have talked about today, you can go to apl.chat and you can grab one of us there. I haven't put our emails here, but if you go down to dyalog.com, you can find contact information for any of us. Just send us a message. Most of us are very nice people. So thank you very much.
Thank you so much, Karta. That was a very interesting and insightful talk. We are a little bit over time, and although I have several questions I want to ask, I want to make sure that people have a chance to grab a coffee before our final session today. So if someone has a quick question that can be answered in a sentence or two, we'd be happy to take it right now. Otherwise, I would ask that folks go ahead and ask their questions during the break. Does anyone have a quick question for Karta? All right, then how about we go straight to the break, and please discuss with Karta there, and I'll probably write my questions directly to you, all right?
Okay, yep, thank you very much. Thank you.